Okay, welcome again to another session. Tonight we're going to talk about LIGO and measuring gravity waves. But as usual, first we'll get to the news. One of the things that are long sought is cheaper to make higher temperatures, closing on room temperature, superconductors. Superconductors being those materials that electrons really like moving through with very little loss due to heat. So superconductors have been something we've been looking at for a long time. And they also have this lovely magnetic effect that they have a magnetic field that just makes them hover above things. So the way I encountered it recently on this was I'm preparing for next week's session, which is on quantum computers. Fascinating they are. And they use superconducting and they use cooling in liquid helium. So when I saw this, hey, they found a new kind of superconducting material and it may be critical for the future of quantum computing, I had to include it. Not only that, but they're talking about it being a rare material. So it's lanthanum, platinum, and phosphorus. So it's LAPT3P is the chemical symbols for this new material. It's another one of those, okay, I hear what you're saying. Let's put a push pin in that and see if they ever make it where it's cost effective. They make it in something larger than a small sugar cube, and they actually use it in quantum computers.
What do they use it for?
They use it for reducing the heat loss in electrical circuits. Electrons don't really have a problem flowing through superconductors. That's why they call them superconductors. Okay, there was a presentation on Thursday by a Chinese space official, and he was showing off the next generation of their heavier launch rockets. And somebody said, that looks an awful lot like SpaceX's super heavy booster. Well, I took a look at it and said, yeah, it's kind of like a mouse on a computer. How many other ways can you make a mouse that actually functions as a mouse? Same thing, if you're going to have a heavier launch vehicle that can carry bigger payloads and you use strap-on rockets on the first stage, it's kind of like, yeah, that's pretty much one general looking way of doing it. So I think they're a little wrong when they're thinking it's a copy of the SpaceX Super Heavy Booster, because there's a lot of details in the engines, the Merlin engines and the Merlin vacuum engines and those sorts of things that are, for want of a better way to describe it, really tricky stuff, and it takes a while to get it right. Also, there was another Iranian launch that didn't go well. They are attempting to launch things, and as we've seen from NASA in the early days, what goes up doesn't always go as high as you want. Virgin Orbit, that's the Branson folks, they're targeting another dress rehearsal of their Launcher 1 vehicle on June 30th, or maybe in the early days of July. I guess it's all depending upon whether and if things are working. I don't know that Branson's going to go up in this one, but he's planning to go up in one soon, just like Bezos is planning on going up in one of the Blue Origin rockets. I saw where people are signing a petition that if Jeff Bezos goes up, he's not allowed to come back. Like that will make a difference. I saw where the United Launch Alliance, the folks that make the Vulcan rockets, have pushed it out to 2022. So they must have some problems they're dealing with. Luckily, if you remember from a couple of weeks ago when I announced that, hey, they're letting the ULA launch the old Atlas V rockets instead of the Vulcan rocket that they committed to NASA that they would be launching. And this is another example of, well, now that they can launch Atlas V rockets more, and they don't have to get the Vulcan Centaur working so soon. They flipped it out from 2021 to 2022. So it gave them some latitude. Not to be outdone with the Iranians, the Turkish government is also going to be launching their own things and setting up their own GPS network. Every nation has to have its own one. The last launch that SpaceX did for the US GPS network, they didn't have to do a static test firing of the engine because it was a recycled booster and it had flown before. So now they're saying that a lot of the stuff that they used to require, if you ever looked at the NASA Launch Control Center, they have a whole lot more people sitting around at desks monitoring consoles than SpaceX does. Well, that's because SpaceX does it a little more automated and shoves a lot of those checks out to the actual rocket. So instead of hearing all of the call outs of the various launch directors, you really only need one because all the other ones are done by the computer. And if the computer doesn't produce a green light, you don't get the overarching green light. So NASA's going, this seems to work well. Russia basically is launching a new segment to the International Space Station using their Energia rocket system. I think they're trying to get to the point where they have newer technology in their upper stages to be able to do, I guess, higher orbits. I guess if they want to conclude that they're going to, I guess if they're concluding that they also want to have their own space station, because if they're leaving the ISS, they've got to have their own space station, because otherwise they're going to be left out because China has theirs, we have ours. So Russia would like theirs. So they're preparing their launch vehicles to be able to launch heavier components. And SpaceX is producing a new drone ship. And the new one is called a shortfall of gravitas. They always have cute names for them.
Yeah. Last week you talked about, them being out there and having another space station was a good thing, right? Because
Yes.
if you had to have a backup, that's a good thing. But there is one drawback, I think, because we were also proud of our interactions with other countries and how the astronauts got along on all these different projects.
Yes.
I hope that was true.
Yes, the Apollo-Soyuz missions go back to the midst of the Cold War. It was a feather in the cap, so to speak, to have had the US and the USSR actually docking and friendly greeting and talking to one another that long ago. And, just because things start to deteriorate on the ground doesn't mean they should deteriorate in space.
But this will make us more distant with having them have their separate.
Yes. I think we should have turned it the other way and say, hey, China, would you like to be part of the ISS? And if so, is there anything you'd like changed? So, we would have one entire planet space station. And as that one got older, the entire planet would build another one. But it sounds like all the major powers want to go their own way. They want to have their own basketball.
Yeah, but they won't have Chinese food.
I've been to China. You know what Chinese food is in China? Food.
Yes, but it's different. I've been to China twice, and yes.
Yes, and in the US, we have this thing called breakfast food. In China, they don't have breakfast food. They just have food.
Yeah, noodles for breakfast. That's right.
Yes,
That's
yes.
right. And porridge. Yeah,
Yes.
that's
They
right.
had bean, those little bean things that were.
You mean tofu?
No. They were put in a dough, and inside
Yes.
it they had beans.
Well, we call them pancakes, but they don't call them pancakes. But
I never had one here. I never had one here.
yeah, they're rice pancakes. They're kind of like crepes made out of rice instead of wheat. Uh,
Well,
but
you went to the richer place than I did. Well, mine was a school that I went to the school over there in Shanghai. I was learning acupuncture and Oriental medicine.
oh, cool.
It's very interesting. But anyway, it was different, the food.
Yep.
And
And the European Space Agency's Ariane group, they're delaying their launch of their Ariane 6, their next bigger rocket, until 2022. So it seems to be thematic to, oh, good, the pressure's off. SpaceX is going to do all the stuff in the meantime, so we can go off and make our next bigger rocket next year instead of this year under pressure. And
We hope
Hubble,
for the Unicorn Space Web telescopes being launched successfully.
well, yeah, I've got a little item regarding James Webb for later this year that maybe next year. Hubble is still having problems.
Don't jinx it.
Hubble is, I did worse than that. We'll get into it. Hubble is still having problems with its payload computer. The payload computer is the one that governs the basic positioning and orbital characteristics of the spacecraft, the overall health of the spacecraft, and not the science, the imaging and running the image coolers and stuff like that. That's done by other computers on board Hubble. But the general computer is having a problem. And I didn't know this, but this week they fired up the backup general computer for the first time since Hubble was ever launched. And they found out it's got the same problem. When they go to a certain memory location, it causes the computer to go into safe mode and shut down. And now both computers are doing the same thing, which is a little strange unless whatever radiation dose Hubble got affected both the primary and the backup computers. Years ago, they did studies on radiation exposure of memory chips on computers, and they found out how to organize the memory arrays to make them less susceptible to catastrophic failure. So I think they're going to be going back and looking at, okay, is this a software bug? Or is this just, well, Hubble got hit by a radiation spike that took out both of its general computer memory boards because they were in the same place on the spacecraft. Like if one was sitting side by side with the other, as opposed to in another part of the spacecraft, then if you had a radiation dose that hit that spot, it could take out both memory boards and not just one of them. So
Software bug.
For a computer that you haven't started since Hubble was first put into orbit and it has exactly the same problem, yeah, it sounds more like a software bug. Adam and I would know, we've diagnosed these things before. Okay, and years ago, they took radar imaging. Now it's false color because it's in radar. False color radar imaging of Venus. And they went back and studied them in more detail and noticed that, when the images don't line up when you're trying to stitch things together, it can be because your camera wasn't set up the same way, or it can be because things moved. So what they found out is that parts of Venus are actually cracked and slightly moving, which would say there's tectonic activity going on Venus. Now, for a planet that is so hot and has so much vulcanization, so much volcanic activity going on, so much lava below the surface, to see that the upper levels of rock are floating on lava, it's not surprising. And after only 3 spacewalks, they finally got the new solar panels working on the ISS. The first time they had a problem with the way in which they were doing it. The second time they had a problem with their spacesuits. So third time's the charm. They are producing electricity now. These are replacement panels for some of the earliest panels on the ISS, which are decades old, and they get exposed to all kinds of micrometeoroid impacts and dust and solar radiation. So it's good to replace them periodically because you can have newer technology that produces more electricity and maybe more reliable over time. So
Did
it's
you
good.
figure out what they're gonna do with the old ones?
No, once again, it's the elephant in the room. They don't really say. And what when you
Because
disconnect
I look
the old
around and I couldn't find it, and then I forgot about it.
the new panel is in the same place the old panel was. So I've got to believe they kind of cut it loose and pushed it away.
I don't think that's safe.
I think it's a
Maybe
question. I think
maybe
it's a
they could have locked on the spacecraft that's gonna burn in the atmosphere.
then that would give it an uncontrolled orbit for reentry. But also these have been extended and locked for so long, they're not going to fold back up. The new ones actually roll up like a carpet. These older ones actually were like awnings, like foldable awnings. So I don't know what they did with them. It's a good question though. If I ever get in contact with somebody at NASA about it, I'll have to ask, like, what did you do with the old ones? Oh, we
Where
just
the
threw those away.
where the trash goes.
Yeah, we just threw them away. That was a pretty large object for you to just like discard.
I thought I saw them on eBay.
Yeah. Did you discard them really hard downward? Did you find an opening, a window in the orbits and, push them downward that way, or? Don't know, but it is a question. And speaking of stuff on board the ISS, how many people knew that the clothing that the astronauts wear for daily use, basically shirts, pants, socks, and underwear, they literally wear them for the better part of a week, despite doing an hour's worth of exercise every day and getting sweaty. So by the end of the week, people get aromatic. They can take showers, but they have to put on the same clothing.
No laundromat.
Yeah, they have no laundromat. So the prior practice until now was they ship new clothing up to the astronauts on their resupply missions. And there's about 120 pounds worth of clothing on every cargo resupply. That's a lot of weight. When you've got 5 or 6 astronauts on board the space station, that's a lot of clothing. If every week you're going to get rid of one and you're only going to be up there with a cargo resupply every 6 months, that's a lot of stuff.
So
So
that's why they say that the space station smells like dirty socks.
yeah, it's like a B-52.
But there will be one more thing to talk about with the Boy Scouts. They're gonna love it. The example of not taking a shower.
Oh, it gets better than that. NASA is working with Procter & Gamble, the people that make
Aw.
Tide laundry detergent.
Yeah.
And they're coming up with a new formulation of Tide to be able to clean their clothing in a Tide designed ISS approved washing machine. And the water that they use in the washing machine will be tomorrow's coffee water.
Yummy.
So you
One
have
more
to
thing
have,
on the list of things to say to Boy Scouts.
yes, talk about you. Not only is tomorrow's coffee today's coffee, but tomorrow's water is yesterday's laundry water.
Very appetizing.
Yeah. But
Anybody wants to go to space again?
no, if you're going to be on board the ISS for an extended period of time, like a year, you need to think about these normal human recurring things. The one that comes to mind earliest is the toilet, because without that, you're only good for a little while. But once you have the toilet, now how long are you good for? Well, until you run out of food, water, oxygen. Well, the water you're recycling, the percentage of the oxygen you're recycling. What about the clothing? Well, just ship up new ones every so often.
That's not gonna happen if you
There's
go
no
to
shipping
Walmart.
up to Mars.
Yeah, same thought.
There'll be another heavy mass to send to Mars, the washing machine. How do they dry the clothes once they've washed them? They hang
Get
laundry in
outside.
the ISS?
I get
And-
outside.
This isn't going home to their spouse to clean, right?
Yeah. Well, I think what it's
Always.
I think what it's going to be is they'll come up with some kind of very high pressure wringer to get all that water out of the clothing, because that's more water they can recycle rather than lose.
They're probably happy about this idea of shipping their stuff off. They're probably not happy about the idea of having to wash their own clothes.
Oh, no. There have been many complaints about the aroma because different people sweat different amounts. And
Yeah.
some of the astronauts are more odoriferous than others by the end of the week, I'm sure.
And so they'd have to wash their clothes more often, somebody, where now they have the excuse that, we can't do that.
No.
And you have to exercise for 2 hours every day.
No, think of a fire station. A fire station is a good closed community example.
Okay.
If you don't have an assigned chef at a fire station, the food preparation duty cycles. Different people do it during different shifts and different days of the week. So if you have laundry and only one machine, that means you're probably going to cycle who does the laundry for everyone.
Oh, okay.
That's the most efficient way to do it. Why just do only your batch in the washing machine when you can put in 3 people at a time, maybe?
Oh, okay.
So you have to think about that.
So somebody was going to fold your panties.
Well, I
You
think
wear one.
if you look at the standard clothing for astronauts, there's not a lot of luxurious undergarments. I think everything comes down to boxer briefs.
But pink ones.
I don't even think it's that. I think they're all black because
No, I think they're all gray, like, Star Trek kind of thing.
I think they're all black because occasionally you'll actually see some of the astronauts floating around the ISS, and it's like, okay, you don't have long pants on, you do have socks on, you do have a shirt on, but you can see this guy's picture. His shirt has color to it, his pants have color to it, but when you get to the socks, they're black. So I think the undergarments are all basic black, and they're kind of like one design for everyone. So in case, because when you're changing your clothing and you're changing your outer clothing, you go with the military approach of, you wear your undergarments and you change your outer garments in front of everybody.
And you have your name and everything.
Yes,
Maybe, I don't know.
hopefully.
Maybe,
First
I don't know.
grade.
Well,
Well, if you
you don't
wanted
have,
clothes, you want them to fit.
well, that was one of the problems they were saying is different people have different fitting clothing. So I don't think they have an actual small, medium, large, extra large, double extra large. I think they probably have a small and a large and a double XL. And
It's much easier to tell which piece of clothing is yours than say by size. You have to compare it to everything and pick it up. Much easier if you have your name in it.
It's
Well,
much
I don't
better.
know,
Yeah.
because on the resupply mission, it's a good question. On the resupply missions, they probably have pre-packaged clothing with the name of the astronaut on the packaging.
Okay.
But, once you've got your lot of clothing up there, it's kind of like being in the military that, okay, you were issued clothing. You have to monitor your own clothing, keep them clean.
I was in the
Regular
military.
member.
When I was in the military, you put your name on it. Otherwise,
Yes.
you lose
Right.
it.
Right. But you're responsible for them, even if you put them in a shared laundry.
Right. But
Yeah.
you're responsible for your name to be on it so you can get it back. you don't
Yeah.
have your name on it, they wouldn't guarantee. Well, they didn't guarantee you get it back anyway.
Yep.
But more likely.
Yeah.
But it's like being a kid, little
So
kid.
Helen,
Yes.
I had heard that one of the really unpleasant things about being in space or any place with zero gravity is that you can't burp. Because there's no gravity, and it would seem to me that it'd make you feel really sick if
Yeah,
you.
no, they feel bloated, like,
Yeah.
really bloated.
Yep.
So it's like your body takes some time to get used to it. Some people have really problems like reflux and all, but some people adapt with the time. So, like the first days that you're in a space station, that is another thing that is bad, is that you go to sleep and you have your reflex, like you slap yourself, and then you wake up and you scream in your colleague, "Why did you slap me?" I'm like, I wasn't even close to you, because you're slapping yourself because there is no gravity and your body is getting used to it. And the other thing is that as you sleep and you close your eyes, you see lights of cosmic rays going through you, and then you see like shiny lights, and then you go like, who turned on the lights? Who took a picture? And it's inside your head that you've seen that.
That's
What if-
human physiology, Cherenkov radiation.
Yeah, but the gas that people get feel bloated because that's one of those things.
Yeah, I mean, for me, I get it, and I have reflux sometimes. I take stuff, and it would just be terrible. I wouldn't want to go to space. What about farting? Can they fart, or is it the same? And if they do,
They
because
do a lot
the
because
opposite
as
reaction, do they get pushed around the room every time they fart? And if they eat beans for dinner, then everyone is farting and getting
yes, everybody's
all
gonna
around
get
the
used to
room.
that sweet smell
Yes.
Isn't somebody
because it circulates.
now? There was somebody that was supposed to be experimenting. Monroe, you mentioned about that somebody was going to do that and see how far they could get across the room or something. Didn't
I
you
don't
say-
remember the detail. I'll feign ignorance. I don't remember the details about that, but it
But
would
you
be it would be something that I'm sure that astronauts have done.
Just cause.
Yeah. All I can say is when you have 4 to 6 guys on board the ISS and no women,
All ex-military.
yes.
Yeah, you're gonna talk
Yeah,
about
I
that.
think NASA already knows about fart propulsion.
Like you curl your body and you go and see how much you move.
Yes. Yes. But you have to learn that East Asian Zen thing of how to press the gas out.
Yeah, but because you're just your saliva, what you eat, as you breathe, you accumulate gas, and
Yeah.
then those natural little burps that come out that you don't even feel it because it's natural, your peristaltic movement.
Yep.
In that case, you end up feeling bloated, and then you wait long enough and it's gonna come out.
I'm sure that there's been the occasion before they put the hammocks in that strap you to the wall that you go to sleep on one side of the compartment and you wake up on the other side of the compartment and wonder how you got there. In the middle of the night, you had a little propulsive maneuver.
Yes.
Okay,
The
enough
thrusters were
about
on.
that. Enough about that.
The thrusters that were on.
Yeah, save it for the Boy Scouts. So this week, I did a couple of things, and I was on the monthly episode of Drake's Lounge for the Society of Amateur Radio Astronomers, where I, pointed out that, hey, we're going to be talking about LIGO. Now, this is a bunch of radio astronomer guys, and they said, good, can you make one small enough that we can, have a beginner's program? No. LIGOs occupy square kilometers. So no. The other thing that I was on last night was on the Denver Astronomical Society, where David Levy, the Shoemaker-Levy comet watching astronomer. He did a presentation, and that was interesting to watch the history of how he did it, and how without having any sort of technical degree in astronomy or technology, he wound up being a person very noted for finding new comets and those sorts of things. And that's just what he fell into back in the day, and that's what he's doing. And he's written, I think, more than a dozen books. So it was an interesting presentation. And then also during the week, thank you, Adam, for this one. The former Jack Horkheimer had the program on PBS, and the program is now called Stargazers, and it's still on PBS. And they had a presentation called Earth's Wildest Telescopes. And they had a couple of people presenting that are the actual leadership of things like the Rubin telescope, the James Webb Space Telescope. And so Adam sent me the link, and I said, this sounds interesting. And I jumped on, and I didn't notice when I started putting out comments that I was showing up as my Broward astronomy person. And they were going like, this, don't know who this Broward astronomy is, but they ask a question. And so it started showing up, and this is a screenshot from it. You can actually see that I started asking questions about, they were talking about LIGO and, gravity wave detection. And I said, what about those new kind of detectors like China has? What? Huh? They didn't know about them. And then later on, they started talking about the Hubble Space Telescope, because that's the precursor to James Webb. And have they looked into the James Webb to see if it has the same software or electronics design issues as the Hubble? Wouldn't want to launch the James Webb, put it way out there at the L2 point, and find out it's even more exposed to radiation and has the same Hubble problem. So take a look at that. So it was, I got the congratulatory, that was an interesting question kind of thing. So I've subscribed to their Stargazers channel on YouTube. So I'll see if I can join some in the future. And I think I mentioned this previously. In July, I'm scheduled to do an interview with the guy that leads the Broward County Library Creation Stations web presentations. So we'll see how that goes. And then I think it's September, October kind of time frame of this year. I've actually received, they put out a solicitation for who would like to host a James Webb Telescope Institute community online session. Sure, I can do that. They sent me back a, sure, fill in the information. You could host the session. Okay, I'd like to host a James Webb, telescope overview session. I'm sure what it is I would be a moderator, and they would bring on some really experienced people like this person that you see here to discuss the James Webb Space Telescope, and I could stick my 2 cents worth in. Don't know if they'd appreciate that or not, but okay. And lastly, yes, the US's Unidentified Aerial Phenomenon Report came out late yesterday, the UFO report. And much like it's been, telegraphed, they said, yes, these have been detected. No, we don't know how they're doing it. No, it's not our aircraft. And could be other governments like Russia and China. So they didn't say this part. Be afraid, be very afraid. And oh, by the way, give us billions more in defense money, just in case we need to build something new. But no specific evidence of extraterrestrials, not really even mentioned as a possibility, just off the table. And of course, when they were doing interviews about the press release of this, they had to get Neil deGrasse Tyson involved, who's, let's just say he's not a true believer. So until I guess an alien walks up and says, "Hi, Neil," nothing exists for him. And
So it was basic something like those droids are not the droids you're looking for.
yes, yes. It's another example of, is it disinformation when they actually put out the information but won't admit to it being them and won't admit to not knowing what it is? If you're the, let's say you're the multi-hundred-billion-dollar military for a country the size of the US, there's a couple of things as a military you would always want to have a good handle on. Who's your opposition? How big are they? What capabilities they have that you don't have? And how would you defend yourself? So if we're sending up aircraft to go chase them around, and we can get, infrared pictures of them, and they suddenly just make a left turn and disappear at multiple speeds of sound faster than we can accelerate, I would say they don't have to be an enemy and attack us. They're an unknown. They really exist. You did track them. They're not birds. They're physical. You don't know how they do it. You should. And if you don't, go do it. So I guess that's the end result of this report is, if it's an unknown, we're going to need billions to make it a known. So sign the check. So maybe that was what it was all about.
The other thing I found that was advantageous for people to start talking is that some of the people who I know in the military and other countries, that whenever they see something, they're afraid to do a report because they're afraid to lose their wings.
Yes.
It could be commercial pilots, it could be military pilots, or people who do other kinds of research observing the skies or the oceans. And then they're afraid to do those reportings, afraid to lose their wings, to lose their, patent, the position. So at least now they are less afraid to do a report like that.
Yeah, in fact, they're doing
Hopefully.
interviews on TV.
Yeah, I think in fairness to Neil deGrasse Tyson, all he's doing is all he has is the same orthodox view of Carl Sagan, that until there's evidence that's reproducible, that you don't really know it. And in fact, Neil deGrasse Tyson says, do spend the money to study it, but and that that until you have something that's reproducible or some physical evidence, that he personally isn't going to invest the effort in studying that instead of studying something else.
Yeah, but I'd have to take his approach and say, does the B-1 bomber exist? As an individual in society, does the B-1 bomber exist? Have you ever seen one? Has one flown overhead? I don't have any evidence that they exist. I've seen pictures of them, but they're not really good pictures. So,
No. I don't think it's the same thing. I also wasn't in ancient Rome, but it's also another well-repeated argument. And Carl Sagan's take on that is that you don't have to have lived in ancient Rome to believe that people spoke Latin or that there were Roman armies and so forth. That they can, it doesn't mean that you can that you personally have to have seen it. That I wasn't in Vietnam, I wasn't in Germany in World War II, but I believe those things exist because there's sufficient documentation, and only it's a question of how much. Certainly, it should be investigated, but when every case where people claim that they met an alien or were abducted by an alien or something like that, they couldn't, where these aliens are so much more, well, first of all, they would basically need a technology where they could travel faster than light, that over the expanse of time that they would need to exist between the time some civilization invented radio waves and destroyed itself with nuclear power or pollution or something. Aside from all those things, all of the easily verifiable claims by picking up any piece of anything from one of the spaceships which would have different kinds of amalgams or different kinds of chemistry than we would have produced, since none of them have been done. It's just I think that it's viewed with a greater amount of skepticism. I don't think it's fair to say that since I didn't see it, that as Neil said, granted, a lot of people said they saw it, and a lot of there were a number of cases picked up by these cameras, which are sensors, I guess. But until it's reproducible and you can have harder evidence, I think it's a question. He's only saying it's a question of what he would personally look into. But by all means, we should spend the money looking into it.
I think it's a perfect example of, if you don't want the answer to be what you don't want the answer to be, you can arrange that. You know, the concept of, well, it can't possibly happen because we can't go faster than light. Really, you're limiting them to our level?
No, of course not. I'm only saying that it would be a necessary prerequisite for them to do
Yes,
it. That's
yes,
all.
definitely.
I'm not. I'm only saying that, you know, extraordinary claims require extraordinary evidence. And again, to me, Neil deGrasse Tyson didn't say any of that, because every single thing he's saying is something that Carl Sagan said. It's
Yes.
like strict doctrine and in science, candle in the dark. Carl Sagan documented all kinds of things and all kinds of different behaviors, and all kinds of things that, you know, people believed that, you know, even though I never saw a witch, there's really witchcraft, you know, because after all, somebody saw somebody pull her sock up, and then there was a storm and it destroyed my uncle's tomato crop, right? So, and those things were shown not to be so. So I think it's only cautionary to find evidence. That's all. That's all. I'm not saying those things don't exist. And Neil deGrasse Tyson didn't say anything that Carl Sagan didn't say. And
Yeah.
I think he's a logical fella.
I think we ought to go back and investigate that burning bush a little more. Because
yes.
I know modern technology.
I think I saw one of those in a fake fireplace once. Yeah.
Yeah.
We are talking through a burning bush.
Exactly. Any other news items?
I appreciated the news today. It was very good.
Eileen didn't make it. She had sent me something about, is there a new age of the universe? And I went back and said, I don't remember seeing an article about that. Still 13.772. 13.8. No, I think that's rounding.
I think
it's 13.772 plus or minus 80 million years.
I like 8.
Not 6 days.
No,
I think
not 6,000.
I think it might be because they're looking for using some of the arrays in Chile, and also adding the Subaru to try to map the first stars already in the beginning of the first galaxy. So that what they are saying is that not a new age, but where it starts the new age of the universe, because you have the Big Bang where everything was ionized. Then you have the time of the inflation and expansion. And then when you have cooling enough to form the first atoms, then you have the deionization of the universe. And this period is the dark ages. We have no stars, you have no energy other than the leftover energy of the first ionization. So that's the microwave background that we see today. So there was a point when you start seeing the first stars, and that's what the new age of the universe is, reionization. So what they are trying to do, pinpoint precisely when the new star started. So the idea is 250 to 200 and to 350 or so. So even in the maps that I used to teach at Fox and the new, we know that the age of the reionization from the last studies was 380,000 years to 450,000 years or so. So it's lowering down the ages of the first stars. And we already know that even before those first stars coming about, the collection of clouds were organizing and forming the first seeds of the galaxies. So galaxies and the first stars were forming together. So might be that what she mentioned, the new age of the universe is the new age of the universe that we know. We are just changing the dates of it. It's becoming more precise.
I asked her to send me a link to whatever article she was reading. Maybe we'll see that. So tonight's session is going to be on LIGO and measuring gravity waves. Next week's session is on quantum computers. And the following session, I'm working up something on US commercial spaceports. And I picked up a new electronic gadget this week, very, very tiny, about the size of a mechanical pencil's eraser, about that diameter. It is a silicon photodiode that measures extremely low levels of light. It can deal with nanoamperes, as in billionths of an ampere. And you connect these things up to a circuit, and you can measure the output voltage. And what I'd like to do is to create a water tank kind of Cherenkov radiation detector out of a thermos bottle. So, you know, we'd have something to look at. And if the detector inside the water-filled thermos bottle detects any kind of light, it won't be because it came through 2 layers of stainless steel. It'll be because a muon went through the 2 layers of stainless steel like it was nothing and interacted with the water molecules and caused a very brief, very low intensity light flash. So it would be a project for the future to just look and play with that. And I've got to say that I happen to be browsing around on Amazon, and when I found out I could get them for roughly $1 a piece, I had to buy them. I bought a 5-pack of them, and I tried them out in what would essentially be as dark as I could get it. And I had to wait for my eyes to adapt. And then I had to put a little light on my multimeter to get a readout. And I had one of these sensors wired up inside of a cover, so no light, no stray light getting into it. And it was still reading 28 milliamps through that. Now, my guess is it was probably infrared that was picking up, because this particular photosensor will detect photons from ultraviolet all the way down through infrared. So it'll be interesting to see
Prime Day sure is amazing.
what we can do with that. Let's play with a new toy. Somebody also suggested, well, why don't you build a LIGO? I've got lasers. I can buy a beam splitter.
So
I don't have
when-
liquid helium to cool the detector.
Monroe.
Yes.
When the first result of LIGO came about, I think Brian Greene went to Kober and brought like a simile model of the LIGO with a green laser. He had like a semi-transparent mirror, and he had the emission coming in back and forth. And then when it came forth, it flipped the wave, so no light was coming about. But when Brian Greene shake the table, you could see the light of the laser. So take a look for, it was the date from the first result of the LIGO, and Brian Greene, I think he was on Kober, if I'm not mistaken.
Well, I remember that they started working on LIGO in the, I guess it was the mid 1990s. They worked on the design of it. And they didn't
No, it was
actually have,
like the last 4 or 5 years. What's the recent results?
I know, and what I was going to say was, it took them the better part of a decade to get all the bugs out of LIGO, all the things they had to pay attention to get a null result, because they were thinking it would be, pretty good detector, and it was an overly sensitive detector. It was detecting everything. They couldn't get a zero reading, basically. When is it not detecting? And then they went back and found out that there's maybe a dozen things, and we'll go down the list, maybe a dozen things they have to pay attention to. And there were things like when airplanes fly overhead, the concussion of the air actually hit the tubes, the concrete walled tubes, and that vibration made it into the steel tubes, which are evacuated, and that caused the detectors to go off. So LIGO is very, very sensitive. Okay, so by now people have heard about gravity waves. High gravity fields like planets, that's a stars, it should say stars, distort the fabric of space-time. Bigger stars that have more gravitational field are neutron stars and black holes. However, their distortion of space-time is essentially static. It doesn't ripple by itself. But when you get two of these very high gravity fields oscillating around one another, they create waves and distort space-time as ripples. If you think of it as, if you had a sheet of rubber onto which you had two spheres that were orbiting very heavy, very quickly, it would create ripples in the rubber. And that's essentially what's happening in space-time, is you have these two high gravity field objects that are rapidly rotating around one another. And that's what's creating the ripple effects in space-time. Now, these distortions, as they're moving and the two objects are closing in on one another and going to collapse into one, the frequency of the waves goes up. And as soon as they collapse together, you're back to a stable gravitational field and it stops. I've actually got a sound effect of that later on. So these ripples in space-time go out in all directions, and they go across enormous distances, as in, the category of could be coming from another galaxy easily, but could also come from our galaxy. If you're not really near the actual source of the distortion, you probably won't even feel it, because gravity waves have been passing through us and this planet for a long time. And until we built detectors, we didn't even know we could measure them. So when they do detect them, it's not like an earthquake that they could feel. They never felt it. They're extremely low in amplitude, strength, and they're very, very brief, on the order of nanoseconds. So you have to be watching for them at all times. Now, gravity waves are not electromagnetic radiation. They're not photons. They're not radio, they're not light, they're not UV, they're not infrared, they're not X-rays. They're literally another kind of measurable thing that does not involve the electromagnetic spectrum. So if it's not electromagnetic radiation, how do you detect it? So on the left, we have our stable, large gravitational field. I couldn't find a good one of a black hole. I wanted something where you could actually see the object. Black holes are like a hole and you can't see the object because it's unlimited gravity. And on the right, you see we've got our two objects of high gravity field oscillating around one another because they're going to collapse together. So they create this ripple action going in all directions. But first, what is LIGO? LIGO is an acronym. It's not the name of a person or something. It's an acronym. Laser Interferometer Gravitational Dash Wave. That way you don't have a W in the acronym. Observatory. LIGO is not one thing. LIGO is two things. There are two gravitational wave observatories in the US. One's in Louisiana, one's in Washington State. And the pair of them are called LIGO. So there's LIGO, Louisiana and LIGO, Washington, or they use the city names as opposed to the state names, which gives you no point of reference. I had to go look them up. So what is a LIGO Hanford? Oh, that's the one in Washington. Okay. They have the same basic design. There's a couple of minor tweaks different, but they have the same basic design of a Michelson interferometer. We'll get into what that means. Okay, here comes lots of words and numbers. Gravitational waves are something we detect at the subatomic level of space-time fabric distances. And we detect them using two very long light paths that are at 90 degrees to one another. They're like a giant L. So as these light paths get stretched or squeezed by the ripples in space-time, that means the length of the tunnel changes where the beam is moving, but the beam itself doesn't change, so it makes a difference. And if you have these two beams out of phase with one another, you can create this interferometer, interference pattern, think of it. If you have the two of them and they're not exactly in phase and they're not traveling the same distance, you have an interference pattern that emerges. But if they're exactly the same length and nothing disrupts them, and you have one that's 180 degrees opposite the phase to the other, then one cancels the other out.
Yeah.
So the laser gets a little exotic. They start with a 200-watt near-infrared laser. They run it through a 90-degree beam inverter splitter. So the beam gets split into two beams, and one's out of phase with the other. You can think of it as flipped upside down. The two beams run down individual 4-kilometer or 2.5 mile long tunnels that they heat, and then they evacuate, put under high vacuum. The tunnels are actually tubes. They're 1.2 meter diameter, spiral welded. They're not just like joined together plumbing. These are actually welded, kind of like a toilet paper tube, as a spiral. And we'll get into why you would want a spiral. They're vibration isolated. So, you know, trucks driving around don't bounce it. And the lasers bounce off of mirrors. There's one mirror at the end of each one of these tunnels. The mirrors are 13.4 inches in diameter. They're 0.1 square meters in size. They're 8 inches, little under 8 inches thick. They're 7.8 inches thick, and they weigh 88.2 pounds apiece. So you have these very heavy, not too big mirrors, one at each end of these tunnels to bounce the beam back. So if you get the two tunnels the same length and you get the mirrors positioned at exactly the same distance down each tunnel, and you have the beams out of phase with one another, then when the beams bounce back and come back to the center, they should cancel one another out, and you have no interference pattern. So
Out of phase by 180 degrees.
yes, out of phase is 180 degrees on the sinusoidal waves of the light that you're sending down the tunnels. So anything that comes through to the detector that is not nothing must be because one of the two tunnels had a difference in length. You know, the mirror at the other end was a little farther away. Now, how much farther away? They can detect a difference as small as 1/10,000th the diameter of a proton. Very, very tiny. Compared to light, they're measuring at 1 × 10⁻23 meters, and light is hundreds of nanometers, which is 1 × 10⁻7. So you're talking about measuring differences that are not only much finer than a human hair, much finer than light, much finer than the diameter of a proton. So there's a lot of things you have to pay attention to get that precise, reliable, and repeatable. So this shooting the inverted beams down to the end and bringing it back and checking the difference with a detector, that's the interference pattern delta measurement. That's the Michelson interferometer. There are other kinds of interferometers. So here's a graphic and a picture. The picture on the right is of Ligo near Livingston, Louisiana. And you can see at the bottom, there's a road that drives up to the complex. It's out in the middle of nowhere. Off to the left is one of the two tunnels. Going to the north is another one of the two tunnels. And you can see they're precisely at 90 degrees. So on the left, you see a diagram. The laser comes in, goes through a beam splitter. You get two beams out of it. The beam goes down the tunnel, bounces off the two mirrors, comes back to the center, goes through to a detector. If they're precise, then everything gets canceled out. If there's a disruptance of any kind, then you get something in the detector, and you have to figure out, did you detect a gravity wave or was it something else? Here's the actual picture of the big stuff. So on the left, you see the laser. The laser has its own room, and then the beam comes out of there and goes into the splitter. Down at the bottom, you can see the size of the beam splitter and detector. It's like, you know, a big piece of equipment. Now, since the detector sits behind the splitter, you have to have the two objects coincident. In the center, you have one of the two mirrors. And you can see it's kind of hanging in a frame. I'll show you the details of that frame. Down at the bottom is the evacuated beam tubes. And you can see they have rings around them. The rings are not for joining the sections. Those are actually welded. The rings are for basically keeping the pressure up because they're under vacuum and you don't want them to collapse. So they have to be spiral welded, and then you have these compression rings on them. And then in the upper right is some of the electronics. You have so many racks full of equipment that people can hide inside the racks and poke their head out for fun, which is what that guy did. But you can see that there's the guy there working some of the computer stuff for it. This is just the control electronics. They have, you know, individual computers for actually monitoring what's going on and showing the displays. So that's additional stuff. So LIGO be big, expensive, a lot to set up. It's not exactly portable. So if you want to get LIGO right, this is the laundry list of things you have to pay attention to. So the distance from the beam splitter to each mirror must be identical down to subatomic levels. Remember, we're working with 1/10,000th the diameter of a proton. The mirrors must be highly polished. If they're not highly polished, then you might lose one or more of the photons to it going off angle or scattering. So the mirrors have to be very highly reflective and polished. The mirrors must be uniformly highly reflective. The actual number is 1 out of every 3.3 million photons that hit the mirror are absorbed and become infrared light, which actually moves the mirror. If you can think about that. You don't see it, you don't feel it, but it does move the mirror. And we'll get into how much it moves the mirror. So the mirror must be large enough in diameter to capture all the photons that come from the laser. The laser beam will actually diverge slightly. Think of it as if you have your laser pointer and you see that the beam comes out about 1 millimeter in size, and then you shine it at a cloud, it's going to be, you know, probably 500 feet across by the time it makes it up the cloud because the beam diverges. Well, if you've got a laser beam that's a fraction of a millimeter in diameter, by the time it traverses 4 kilometers of length to get to the mirror, it's going to be larger, which is why you need a large mirror to be able to capture all the light that's going down the tunnel. Now, since the beam is slightly diverged and you want to pull it back together so that all the light that's bounced off the mirror goes back to the detector, you don't lose any, you need to curve the mirror just slightly. Think of your focal length. What would be the focal length of 4.3 kilometers? A very, very soft curve. So that's to get the beam back down to a fine point at the other end of the tunnel. And the focal length must be small enough so that all the beams fit inside the detector. No photons going stray outside the detector. In fact, you probably want the converged beam to be smaller than the detector, so you have a little safety play there. To make sure that they've got it right, they actually have calibration test masses, which are kind of mirrors, but they're special kind of mirrors that they can measure basically how much movement is in the mirror. The mirrors are hung from what is known as a quadruple pendulum. So they're not in a frame, they're swinging free, but they're swinging on 4 pieces of glass fiber that are 0.4 millimeters in diameter. So think of it as if you draw out a piece of glass, a heated piece of glass, and it draws down to a thread of glass that's 0.4 millimeters in diameter. That's the diameter of one of the 4 pendulum fibers that the mirrors are hanging from. And remember, these are 88-pound mirrors, and they're hanging from these fibers. Just to add more difficulty to it, the mirrors are cryogenically cooled. These are mirrors that are immersed in liquid helium. Now, why are they immersed in liquid helium is not to keep them from swinging, because they've got other ways of doing that. They use electromagnetic fields to dampen them. This is to keep the temperature of the mirror material itself down to a near 0 Kelvin value, because the atoms in the glass of the mirror need to be not warm, because if they're warm, the atoms move around. You can't see it, you can't feel it, you wouldn't normally detect it, but when you're measuring something down to 1/10,000th the diameter of a proton, heat in the mirror is something that's going to cause false reading. So you have to cool the mirrors down to within a few nano Kelvin to get the atoms to not move around so much. Now, remember me saying that 1 out of every 3.3 million photons is absorbed and becomes infrared? Well, you have to push on the mirror to make that not push the mirror from the other side. So they actually have a laser pointed at the backside of the mirror. A CO2 laser is occasionally fired at the mirror to make it stop moving due to the stray infrared absorbed photons hitting the front side of the mirror. The beam tunnels themselves, to avoid dust, vapor, and air turbulence, they heat the tunnels to cause all the water vapor to all the water to become vapor. And then they spend, I think it's 10 days vacuuming the tubes to get the air pressure down, all the water vapor and the dust out of them to the point where they're a good vacuum. Now, when you build something on the surface of the earth and it's 4 kilometers long, the curve of the earth comes into play. So if you think of where the beam splitter is 4.3 kilometers down the tunnel, and you put a level on the tunnel is going to be level, but the tunnel is wrapping to the curvature of the earth, which at the end of 4.3 kilometers is about a 1 meter height change from the beginning of the tunnel to the end of the tunnel. So the beginning and end of the tunnel are not curved to the surface of the earth. The end of the tunnel is actually raised up and not curved to the surface of the earth, so that the tunnels are straight and flat. And they have closed loop monitoring of all of this, the laser beam, the mirror movement, how much energy is entering the detector, the interferometer detector on the other end. All of this is being measured and feedback applied 16,000+ times a second to keep it all nice and stable within very tight tolerances. Where I first came into encounter with LIGO was when I was studying photonic propulsion. And I found out that LIGO had a problem. In 2010, LIGO had a problem. They upgraded the lasers from about 60 watts to 200 watts because they wanted more photons in the beam. And when they flipped on the laser and it hit the mirror moved at the subatomic level. So when you fire a 200-watt infrared laser at this very highly reflective, very uniform surface mirror, that 88-pound mirror with a surface area of 1/10 of a square meter moves at the subatomic level. So yeah, hey, light makes things move. You get enough light, you can make things move more. They also found out that even though they have this lovely 200-watt laser, the laser produces something called shot noise. When the crystals, when the semiconductors of the laser are firing, you don't always get 100% of the photon output all the time. The temperature of the chips that are producing the photons varies as energy levels within the crystal change. This is called shot noise. Think of it like if you're inside of a building that has a metal roof and it's raining heavy outside, you note that sometimes the patter of the raindrops changes even though the wind doesn't change, even though the general intensity of the rain doesn't change. But the total volume of drops hitting the metal changes. That's shot noise. So if you have your laser pointer and you notice that when you first turn on the beam, it comes out nice and bright. And as the crystals heat up, the beam kind of waffles a bit. That's the same thing. It's shot noise.
Remember my little thing with the laser that makes a
Yes.
lot of noise?
Yes, that was amazing. An amazing discovery about laser pointers was there's electronic circuitry inside of the better laser pointers to actually change the amount of power going into the crystals to keep the amount of beam light coming out so that the beam brightness doesn't vary over time. And we took the light output of a laser pointer that was a 3-watt laser pointer, it was a 1-watt laser pointer in green light, and shined that into a solar cell, into a photocell, and then connected the voltage output of that through to a speaker. So you could actually hear the beam pulsations. And when you first turn on the laser, it would come out. And then as the laser heated up, the frequency of the pulses going to the crystals increased dramatically, and it got louder. So the amplitude was growing higher, and it got very high in pitch. So the frequency was going up. So it's something you don't notice. You just turn on the laser beam and it stays nice and bright. But what's actually happening is it's increasing the voltage going to the chip. And as it does that, it does it more often. So it keeps the beam brightness the same. Something that I found was interesting is when you're trying to sample something that could have a wave duration of 2 nanoseconds, 2 billionths of a second, you have to sample that at a very, very high speed. So if you wanted to detect 2 nanoseconds, there's a little guy called Nyquist that would say, oh, you better actually sample it 1 nanosecond or 1 billionth of a second. So how many samples can you take at 1 billion per second? Well, if you try and do that to a very high precision, like 16 bits per sample, you're not going to get 1 billion samples per second. There's just too much data that needs to be moved. So you have to cut it back to 8 bits. So LIGOs can only detect an amplitude of 256 things, 0 to 255. That was interesting. So here's the mirror. Here's one of the 2 mirrors. This is just a graphic showing all the stuff they had to think about. They have test mass mirrors that are similar, so it's pretty much all the same. You can see they loop around. Here's the 1, 2, 3, 4 glass fibers that are holding it. They actually start up here. And there are 4 of them, so it's a quadruple or 4-segment pendulum. A 2-segment pendulum would not self-adjust itself. If it's 2, then that means you can have oscillations. If you have 4 of them, it's less likely to oscillate in other dimensions. You have a whole bunch of electronics that control magnetic fields, and that's how they dampen any larger scale movements of the mirrors. And they have a laser that bounces off the back. That's a CO2 laser that basically compensates for the infrared heat absorption from the laser hitting the front. So that's the simple mirrors. So I learned how low do they go. Somebody pointed out that the LIGO mirrors are the largest objects ever to approach 0 Kelvin. They're at 77 billionths of a Kelvin. That's about minus 459 degrees Fahrenheit. Very, very cold, liquid helium. Done to slow down the atom movement within the material of the mirror. So how do you calibrate this thing? Well, it turns out they calibrate it pretty much like if you've ever had one of those handheld laser distance measuring things where you point the beam somewhere and it can say, that's exactly 12.25 feet or in meters or whatever. That's exactly what they do. They turn off the beam down the other tunnel. They turn the beam on the tunnel they want to measure, and then they modulate the laser beam so they can detect the travel time down the tunnel and back. And remember, they're measuring to 1 nanosecond accuracy. So they measure it on each tunnel independently so they can filter out false positives. Because remember, they're measuring down to 10 to the minus 23. So the false positives that they had to deal with when they were first building LIGO was building creeps. As the sun heats up, as it cools down in the evening, the building creaks. You may not hear it, you may not feel it, but LIGO can detect it. Lightning. If you have a lightning strike, that produces an acoustic shock wave that shakes the ground. LIGO can hear that in gravity waves. Distant earthquakes. You'll notice that one of the LIGO observatories is in Louisiana, where they don't have as many earthquakes. And the other one is not in California. It's up in Washington State. And it's towards one side of Washington State. So they're not too close to fault lines because earthquakes would trip LIGO. And also, they have one towards the eastern part of the US, one towards the western part of the US, so that if one part detects an earthquake, like the one in Washington, that the same signal will be picked up some number of seconds later by the one in Louisiana. You can go, oh, that was just an earthquake. Cars driving around. If you're too close to a highway, you notice that the one in Louisiana was out in the middle of nowhere. If a car is driving up to the LIGO facility, I'm sure that if the car is driving over a rock road, that vehicle's tires are causing reverberations that LIGO can pick up. Airplanes flying overhead compress the air as they fly overhead and cause acoustic waves. People walking down the tunnels, down the underground tunnels, or in and around the laser, the beam splitter, or the mirror enclosures. So I would guess that all of that stuff is vibration isolated, and that the LIGO control room is in a separate building from the beam splitter and the tunnels to keep just people walking around the building from being transmitted into the concrete foundations. So in the links that I'll post on the YouTube page, there are discussions here about the specs of LIGO and how they calibrate the beam tunnel length using laser frequency modulation. So there's more than just LIGO. Remember, LIGO is 2 observatories. There's Virgo, which is an Italy-France consortium. They have their observatory near Pisa, Italy. There's a couple of smaller ones in Hanover, Germany, outside of Tokyo, Japan, and another one in the Gufu prefecture in Japan. There are 2 proposed space-based. In other words, they had so many problems with these detectors on Earth picking up things. We'll do them in space. And they also had the issue of how do we make the tunnels even longer so that we can detect even smaller gravity waves. In Japan, they're coming up with the Desigo to launch in 2027. They will be triangular in shape. If you remember, the LIGO is L-shaped, but that's because it's sitting on ground. It's got something to keep it from spreading apart. Well, you're not going to have that in space. If you have the 3 points, they're always going to want to shift in another dimension. So you actually have to have a third one, and it makes this triangle, 3-dimensional triangular shape. So that makes it stable. And they use lasers to measure the distance between them. So Desigo is going to have triangular arms that are 1 kilometer. Not too big, but it's, they'll try it out. Then in the 2030s, the EU is going to launch their LISA detector. It's triangular as well. It's going to have 2.5 million kilometer long arms. I don't know where they're going to put them. Something says Lagrange points when you're that far apart. So there's lots of people making these sorts of observatories. If you want to see a laundry list of them, there's a link.
By the way, there is an app that you can have, I have on my phone about LIGO, and you can see all the other observatories and some of the observations and what is real observation or what is likely like noise. That you can download an app on your phone.
Yes, and you can go to the LIGO website and actually look at and listen to their observations, and we'll listen to one shortly. So how do you know where the gravity wave came from? You've got this L-shaped detector, and you've got another L-shaped detector over in Washington. So you got the 2 in the US. Are they both at exactly like, both L-shaped like that? Is it like that? How do you do that? And how do you know what angle things are coming at? Because an L is it on that side of the L or this side of the L? Well, depending upon which tunnel gets longer and shorter by the wave, that would tell you one, but that's like a 90-degree field of view. But compared to the other one, it's really a 180-degree field of view. So how do you align these things and space them? So should an event arrive at only 45 degrees offset to this L-shaped detector, both arms are going to change by a differing amount based upon the gravity wave and which L it hits, which side of the L it hits first. But they're both going to move. So it's not always just one. And don't think of the gravity waves as coming from space. Remember, the Earth is rotating, the Earth is going around the sun. The gravity waves could actually come from the backside of the Earth up through the Earth. And when they come up through the Earth, now you're 180 degrees opposite to your L. So your L's like this. The gravity waves are coming this way. So you need more gravity waves to determine the source. You need at least 2, and having even more would be better. So if you want to detect the event source, that's a good thing, because then you can say, we have an idea that it's about in that direction right now. And once you know that, you can, call up your friends at your optical, radio, infrared, satellite, I should say UV, ultraviolet, and X-ray and gamma observatories and say, are you guys detecting anything at this location right now? So you can correlate gravity waves with other sorts of observations. So when you're talking about optical telescopes and radio telescopes, they only observe during certain times of the day, or maybe they're looking at certain targets at certain times. Since you don't really know where the gravity waves are going to be coming from, you have to have your gravity wave detector on all the time. So you're generating, back to the old petabytes worth of data per day kind of thing, only to find out, well, didn't have anything that wasn't a false positive today. So scrap all of yesterday's data and look again tomorrow. Kind of like those Cherenkov radiation water tanks. You always have to be looking because you never know when it's going to happen, and you never know from what direction it's going to occur. So I drew a diagram here to say, how are they arranged? Because it was these, Virgo and Ligo, the two Ligos, they're all L-shaped. How are they arranged? Well, the green thing is the Earth. They're all on the curvature of the Earth. They're all flat, perfectly flat, otherwise it won't work. I actually went on Google Earth and found out the positioning angle of them and their longitude, where are they on the curved surface of the Earth, and did a comparison. So in the upper right, I have an example of an incoming gravity wave. So you got a gravity wave that comes in. It first hits Virgo, and it's going to hit the right arm of Virgo. And then it'll affect the left arm of Virgo, but not quite so much because it's at an angle to it. Ligo, however, it's going to smack one of the Ligo arms dead on. That's just the angle of the example I've drawn here. It's going to smack that upper arm dead on. So it's going to really compress that one and expand it. But the other arm is 90 degrees to it. It may not affect it at all. And Ligo in Washington is going to be seeing it from pretty much the backside. So it's going to see a different effect. So when you have gravity wave detectors, you have to have a little friendly network of them, because knowing, just one site detected it is not enough to figure out from where it came. So you have to figure out all of this with timestamps that are down to the nanosecond accuracy, so you can measure how the gravity wave rolls over to or comes up through the surface of the Earth. And the reason why you need to do that to such a fine degree is, note that there's a 100-degree separation between Virgo and Ligo in Livingston, but there's only 29-degree separation between Ligo in Louisiana and Ligo in Washington State. So it could happen very fast. Okay, now for the fun part. You've waited long enough. So when a pair of neutron stars is orbiting and they're going to collapse into one another, you get this, they have a graphical of it. So they have a spectral graphic, and they also have just a waveform. So you can see it kind of things starting to interact, and then they get closer, the amplitude goes up, the frequency goes up, and then when they merge, it kind of like drops off. And if you look at that as a spectral graph, you see it kind of gets somewhat busy, gets a little chaotic, gets very high energy, and then just drops. Everybody ready for the audio?
Mm-hmm.
That was it. Did you hear it?
Great. Okay.
Very exciting.
Okay, I'll play it again just in case you missed it the first time.
Awesome.
That's
Wow.
it. You heard a gravity wave.
The sonification of a gravity wave.
Yes, yes. The gravity wave frequency is actually much higher than is human perceivable. So they not only just mapped the wave, they also downshifted the frequency of the wave to human perceivable levels. It's going to be very, very, I mean, if these things only last 2 nanoseconds, you know that wave is going to be very much shorter, and you won't see it as frequency in hertz. It's in hertz because that's what our ears work on. Once you get up about 44 kilohertz, you're not going to hear it. So they went looking for other ways to see gravity waves. Somebody said, well, if you're measuring the distance between 2 points and you're looking for the distance to change, and you're looking for an energy pattern that is regular and stable, what about pulsars? Because some pulsars, which are rapidly rotating neutron stars that are spitting out energy, and when they point that energy towards us, we get kind of a lighthouse effect. You know, we hear the pulse go by. Some pulsars are nanohertz. They're very, very, very fast spinning. And if you measure the distance between the time separation between each pulse, that's extremely accurate. So if all of a sudden your pulsar stretched and then came back to its normal rate, well, nothing happened on the pulsar itself. Something happened in the path between your observation point and the source point of the energy of the pulsar. And that could be gravity waves. So what they're doing is they're creating timing arrays. It's a detection grid based upon measuring a lot of pulsars. If you remember the Voyager records, the way that the extraterrestrials could find Earth was, I think they had 13 pulsars, and the timing of the pulsars were different. So you could say, if I can detect that pulsar and that one, and I change the direction back, it points towards Earth. You are here. Well, they're taking that literally and saying, if I can measure all these pulsars down to nanoseconds, and all of a sudden a pulsar changes, and then I see another pulsar change, it could be a gravity wave moving across my grid of pulsars. So that's a very, very large kind of LIGO, but it's not actually an interferometer. They're just measuring the stability of pulsars over time. The next thing they came up with is spherical superconducting harmonic oscillators. Catchy phrase. That's literally, if you take a sphere and you rotate it at high speed and you have it above a superconductor suspended in liquid helium, then wobble should not exist because it's superconducting. The things that you would normally see like a spinning top, once you make it superconducting and you put it inside of liquid helium, you shouldn't see that, and it should spin forever because it's superconducting and it's in a magnetic field. So they're saying that, well, if it does change, there's something on the outside making it change, and it could be gravity waves. This would be a very much smaller, less expensive, faster to deploy. You don't need tunnels, gravity wave detector. But they've been working on it for a while, and it's not as accurate, not easy to detect as LIGO. LIGO just has the benefit of scale. So you have mini Grail, which is only 68 centimeters across. They can get down to 1 to the minus 20th meters, but not the minus 23rd of LIGO. They have another one that's even smaller. It's only a few centimeters across, and it can get down to 1 times 10 to the minus 17th. That one would be really good at detecting earthquakes, but not so great for detecting gravity waves. Then they came up with this new concept. Instead of having a superconducting rotating sphere, what if they just have a circular chamber in which they're using magnetic fields to rotate microwave beams? So if you shoot a beam of microwaves into this circular chamber and you have a magnetic field, kind of like the toroid donut of a fusion reactor, around the outside, then the microwaves ought to just keep going around as long as you keep the magnetic field up and running. And anytime there's an outside disturbance to the microwaves inside the magnetic field, you're going to produce photons, because you're literally injecting energy into this field, which is got microwaves in it, and the microwaves are going to become energized, and they're going to want to discharge that energy and produce basically radio waves, photons. And so that's the next generation of detectors. They tried one in Birmingham, England. It's only 1 meter across. It got down to 10 to the minus 1 times 10 to the minus 13th meters. Still low resolution compared to LIGO, but this has promise. So what is the effect that they're working with? We know that a Michelson interferometer is what LIGO is using. They're using the inverse Gertschenstein effect.
Manuela, help us.
There's actually 2 scientists that came up with this, and it's the Gertschenstein-Zoldovich,
Oh.
the GZ effect. It's like pronouncing the volcanoes in Iceland. This one's just the GZ effect. It's synchro resonance condition detection. And you have a chamber into which you inject microwaves of a certain frequency, and you put a magnetic field around the outside of it, and you can keep the microwaves oscillating inside there as long as you keep the field going. And should anything kind of wiggle the chamber, you should be able to detect that, because the wiggle of the microwave field will produce photons in microwaves, and those can be detected by radio receivers outside the chamber. And depending upon which detector picks it up, it will tell you the direction it came from. So with a single detector, you can detect presence, frequency, amplitude, and direction. So this is very interesting stuff. They are building one in China, and it's called I'm going to pronounce it wrong, the Chongqing detector in China. And they plan on making this thing at its first phase good to 10 to the minus 32 meters. Remember, LIGO is minus 23. This is going to be minus 32. I don't know how do you say, what's the actual, how accurate is that? That's going to be not 10,000ths of the diameter of a photon, but that's 23, 33 would be 10. Ado, yeah, it would be 1 adoth, the diameter of a proton. And there's all sorts of electronics measurement accuracy things that come into play when you start measuring stuff down to that level. There's a funny number at 10 to the minus 35. You remember that one, Helen?
20,
Minus 35.
20, no. 6,02 vezes 10.
It's the Planck limit. It's the
Yeah.
Planck length limit. Nothing in physics is supposed to be any smaller than 1 times 10 to the minus 35th meters. That's the Planck length. So this is minus 32 and the Planck length is minus 35. That says you've got to be measuring your times not in 1 billionth of a second, but in 1 attosecond. And you may have to create new electronics to do that. But stick a push pin in it. This is where gravity waves are going to be heading. Smaller, cheaper detectors. So what can you do with smaller, cheaper detectors? If you remember the size and the cost of the first microwave oven, the Amana radar range, back when it was used for military purposes, they were big, they were expensive, they were not very efficient and reliable. But that was the first one. What do you have nowadays? Well, you go down to your Target and you spend $50 and you get yourself a 1.5 kilowatt microwave oven for cooking your popcorn and your TV dinners. So let's let gravity wave detection progress as well. So if you could have a smaller, cheaper, more sensitive, and could determine source direction single detector, possibly using one of these circular microwaves, now you can start thinking about making a desktop gravity wave detector. That means you can have a whole lot more detectors. If you could shrink it down to the point where it would become a computer add-on peripheral, you can now start having a lot of research labs studying gravity waves. As soon as we learn how to create these very high resolution, low energy gravity waves, we can modulate them. And in communications, anytime you have a source of communication that can be modulated and then detected and demodulated, we can use it for communication. That's what radio does. We send out radio energy at a certain frequency, and then we adjust how we send that out, either in amplitude or frequency, and that modulates information onto it, whether it be digital data, computer data, or audio or pictures. We modulate it, we demodulate it, we get back the original information. As soon as you can modulate gravity waves and detect them with small detectors, you can now start considering communication via gravity waves. And if you can communicate via gravity waves, that would be much better than radio, because gravity waves would not be sensitive to static noise bursts from solar wind or cosmic background radiation, both of which are in the radio realm. You're still constrained by the speed of light, but if you can start off by demodulating gravity waves, because you have much more cheaper, smaller, faster detectors, maybe SETI should be looking into gravity waves, not just radio and light. Or as I said.
But you might have a static background gravitational field, because you imagine, like, if you're like in a pool, you throw something on a pool, you have the large waves, and then as they reflect around, you have a background of smaller waves until they kind of dissipate. So on the universe, you might have also a background gravitational field, like, small waves, they're, just breaking apart.
Well, LIGO hasn't found those yet. What LIGO
Yeah,
has
they are
found,
too small.
yeah, what LIGO has found is very infrequent. Like if you're lucky, you might get a detectable gravity wave once a year, but it's been a couple of years between them.
Yeah, but you have to remember that what we are capable to detect as big, massive bodies colliding.
Yes, high energy, high frequency, but the amplitude is still small. So I just closed here with electromagnetic radiation communication. In other words, radio and lasers is today's smoke signals. As in,
yeah.
Once we get good at communication via gravity waves, why would anybody use radio? It's kind of like saying, why does anybody listen to AM radio anymore? FM is so much better. And then, why would anybody listen to analog FM radio when digital FM radio is so much better? So once we can modulate and demodulate and communicate using gravity waves, why would anybody ever use electromagnetic emissions for radio, for communications? That's just so old hat.
But you'd have to generate the waves, right?
Yes.
Yeah.
We're
And
just
that
now
ain't
we're
easy.
just now figuring out how to receive them.
Yeah.
But it doesn't mean we can't. It just means we haven't paid attention to it yet. At one time, we couldn't travel faster than the speed of sound, and that wasn't too long ago. At one time, we didn't have lasers. We didn't have orbiting satellites. Or as I like to say, as long as you don't stop me from learning it, I can learn it because I am a polymath. And there are a lot of people out there that, as soon as you show you can detect something and you notice a pattern in that, you may say, is that modulated? And if it's modulated, how do we do that? So as I say, put a push pin in this and keep an eye on gravity wave detectors as they get smaller, cheaper, more plentiful. The consideration of, and now how do we generate gravity waves? At one time for radio, it required these enormous spark gap generators.
Yeah, yeah.
And it was very crappy, and you only did analog communication, and you had to have enormous towers with giant wires between them. And nowadays you have a cell phone with a fractal antenna inside. So things can change if there's a desire for them to change. We can improve, we can advance technology. Don't hold us back.
Yeah,
What we
not
can-
long ago, Faraday was giving lectures on something that will never be used in everyday life.
Exactly.
Electricity.
Exactly. And remember when Leeuwenhoek was showing off the early microscopes, it was an amusement item at his parties. Now we have electron microscopes that are studying the movement of gold atoms. So give us a couple of 100 years. Okay, now comes the speculative part. If we're measuring the distortions of space-time down to smaller and smaller levels, is there something akin to what we had to do with GPS satellites? Remember when we first put up GPS satellites, they were at about 75-foot best accuracy.
That's right.
And then
Yeah.
we realized, oh, the satellites are moving at about 19,000 miles an hour. Gee, maybe Einstein was right. We're getting time distortions due to the fact that they're moving so fast, and we adjusted the calculations to compensate for relativity. And lo and behold, they could get down to nowadays a few feet. So as we're detecting gravity waves to much, much smaller levels, is there some point at which we have to compensate for the expansion of the universe? So, no. If you read through all this math, you'll find out you would have to be measuring the distance between pulsars at about 1 times 10 to the plus 12 light years. And you'd have to be measuring time in yoctoseconds, which is 10 to the minus 24th seconds. So until we can get to that level, now we're safe. More likely you're going to find out that pulsars have stellar quakes that are a bigger noise problem for you than space-time expansion. But it's something to look forward to.
Oh yeah. Just because we can't do it, we're supposing the aliens can't either.
Of course.
They're no smarter than us.
Nothing can be smarter than us. And there is no zoo hypothesis where they're on the outside looking in and we can't see them and touch them. And there was that episode in the Star Trek Next Generation. Who watches the Watchers?
Oh, I just saw today the one that they figure out the puzzle with the DNA of many species.
Yes. And maybe some of that junk DNA is actually data,
Yes.
because we can't find that it's useful for any, genetic cellular precursors. So all these genes,
it's left over from viruses.
right? It's left over from our precursors that aren't supposed to exist. We were born this way. Yeah, you and billions of years of evolution. So
So
any thoughts on gravity waves and gravity wave detectors?
just to help up a little bit, I put on the chat the video of Brian Greene and Colbert. If you don't want to go to the copyright stuff, you go to it's on YouTube, so you won't have problem. It is 3:50 that the experiment starts, but then later on, if you watch the whole video on your house, it's going to be easier because he shows pictures of the waves in space-time moving. But it's cool because this explains LIGO with the laser, so it's really cool.
So-
you can share the video so everyone can
Well,
see.
it's in the chat.
Yeah, but you can share the video and comment.
Okay.
Fun. Especially Scover. He's my news. And then the second link that I placed while you're looking for is the video where you're using your big laser on my solar cell and making that.
Making the turn that thing off. It's hurting my ears noise.
Yeah, hurting my ears noise. You can lower the volume.
Okay, let me share.
He's very smart. And then the other video that I post there was a video of our noisy experiment.
So before we go for the next one, so that Brian Greene presentation was in 2016. So that was a very early LIGO
Was the
discovery.
first one.
Yeah. And it wasn't until 2020 that they had the new high power lasers and the bigger mirrors with the 4 glass fibers holding the mirrors. Back in 2016, they actually used very thin metal rods to suspend the mirrors, and the mirrors had the tendency to wobble this way because there was only 2 of them at the microscopic level. And I think that particular sound that they played had been juiced a bit. If you noticed at the end of it, there was reverb, and there shouldn't be any reverb. You shouldn't hear the deepening echo effect of it. So I think that the folks at CBS might have sweetened the sound a bit. But the one that I played for you was directly off the LIGO website.
So the difference from the old way they suspend the mirrors and the new way is that before we could only detect large collisions of 2 black holes. And now we are getting so precise that we are starting to observe smaller objects, less massive objects like white dwarfs and neutron stars.
Yes.
Oh, there
From
we go.
Sophia. Now we're going to point a blue laser to the solar cell.
Say when?
Now,
It does sound like a... So did you get that?
So the vibration of the light being pumped, it started steady because the crystals are cooled. As they get hotter and hotter, they start to vibrate and vibrate faster and faster. So now the vibration of the light is blinking. And then at that change, that vibration of light is being transformed from electrical pulses that I connect to a AM, little speaker, and makes that noise that hurts your ears.
Yes, that
That
was
what Monroe was doing with his photodiodes.
It's from
No,
here.
this was years.
Now we're gonna point a blue laser.
It's
No,
like
stop.
a tiny little, solar panels with plastic. It's really bad quality. It was like for you to construct little robots with soda cans. So it's
Okay,
really
so
bad.
this little thing right here, that's the solar panel. And you can see this bluish color. That's me. I've got my hands above pointing the laser beam down. I don't make any adjustments on the laser beam. I just hold the button down and the beam comes on and stays on. The goal of the electronic circuit in the laser is to keep the beam brightness the same as the crystal inside the laser heats up. You need to give it more power and you need to literally pulse it at a higher rate, which causes the frequency to go up. So that's what you're actually hearing was the laser.
So when I point the little laser to a fluorescent light bulb, because the electricity here vibrates to 60 hertz, you can hear the hum. You can actually hear the hum of the
So anyway, that's what we do in our spare time.
yes. The genius ideas.
Mhm.
Well, the Boy Scouts always love it.
Well, I was a Boy Scout once, so obviously I love it.
That's my measure of success.
Mhm. Okay.
If they like it, I'm
any,
good.
any more comments or questions involving gravity waves, tonight's presentation, the news, any of those
That
sorts of
was a
things?
very good presentation.
Super,
Yeah,
super presentation. Thanks
I-
so much. Great.
I am no Brian Green, but
Uh,
what I will do is I will send to the folks at PBS a link to the YouTube video once I get it uploaded and edit the blooper reel parts out and see if they like it.
but the cool thing about this is that before 2006 and even a little bit later, we have no way to see the universe from before the deionization of the universe.
Mhm.
So the last light you could see in the universe, it was the background microwave radiation. Other than that, it would be impossible for you to see anything in electromagnetic waves because the universe was too hot and too ionized. So when you have ionized gas, it's opaque. It all looks white everywhere. It's like you're inside a very bright cloud. Everything is bright everywhere. And photons of light, they bounce in, absorb and emit, absorb, emit. So I don't know if you ever saw how photons of light are made inside the sun, that one photon takes thousands of years to come out of the sun because that is a ionized gas, that's plasma. And then the photons are bouncing everywhere and not being emitted and absorbed, emitted and absorbed in all the directions. So from that point when the universe was all ionized, you could say that we were blind to at that era. We started seeing things in the universe when the first stars come about around 400,000 years after the Big Bang. So with gravitational waves, now we have a way to actually see prior to that. Prior to the formation of the first stars, try to see the formation of the first galaxies, the collection of gas falling, if that is some kind of a gravitational effect, and maybe even some kind of not microwave, but gravitational background that was during this time or during the time of the inflation. So that is now is just open a new window that we could see. So like remember before we figure out the existence of ultraviolet or infrared or radio waves, all we could see is visible light. So then the rest of the universe that we could see was invisible to us until we figure out that we can have radio, we can have microwave, we can have ultraviolet, X-ray, gamma ray telescopes that we can see universe in other kinds of light. And
But
then,
those were all the same at the principal level. They were all emissions of electromagnetic radiation. They were all
yeah,
photons.
but the analogy that I'm
gravity is,
making it is that when we discovered those different ways to see the universe, we opened windows that we could see now. That before was just visible light. Now there is a different kind of window that we couldn't even thought about it until 100 years ago, and finally took like almost 100 years for us to make an equipment that could see that kind of information that is not even, we could not even see as light, as that data.
I like
data that's a new window that we can see the universe, and even earlier universe, and that is like my takeout of the discovery of finally proving Einstein correct, and being able to observe that is a new way to see the universe. It's so amazing, because you kind of, now that is another window that you can look. So for me, this is like amazing.
I like to think of it as, prior to our discoveries of other than visual electromagnetic radiation, the universe was carrying on a one-way conversation that we had no ability to listen to.
Nice.
Gravity
This should be in
waves
the
are the
next
same.
t-shirt for the-
Gravity waves are the same sort of thing. Gravity waves have existed forever, and our bodies cannot detect them. Therefore, to us, they did not exist. The universe was carrying on a conversation in gravity waves that we had no technology to hear. So now we have the ability to hear, much like we did with electromagnetic radiation. The moment that we hear it, we start thinking about, can I use it? Can I do something productive with this thing that I just discovered that's been around forever? I think gravity waves are going to be the same thing. We already know.
Eventually it's going to end up in your mobile phone.
Yes, we already know that we can create shifts in gravity, and we do this every day. Think about tall buildings in big cities. Buildings used to sway constantly. How did they stop it?
Rubber.
Mass drivers. Up in the top, mass drivers up in the top of the building.
Oh, yeah.
They have many tons of solid concrete that are sitting on rollers.
Right.
As the building wants to go this way, the heavy gravitational item wants to keep it from going that way, and it pulls against it. So it keeps the building from being too rubbery because of this giant gravitational item. So we're already manipulating gravity and just not measuring it. So as soon as we can get gravity wave detectors to detect smaller, lower amplitude, higher frequency gravity effects, maybe we're going to have a background noise of, gee, I wish they'd stop building those tall buildings because it's interfering with my gravity wave detectors. Kind of like the Green Bank radio telescope is built out in the middle of nowhere inside of a ring of mountains, and you're not allowed to drive a car to the site if it has any form of electromagnetic communication in it or advanced like computers. You can't carry a cell phone. You can't even carry a GPS receiver.
You cannot mix. Okay, that what you said is an awesome analogy, but mechanical wave is different from gravitational wave. You cannot mix one with the other, because mechanical waves needs a medium, and gravitational waves don't need a medium. Space-time is the medium.
Is the medium. Yeah.
I think you're thinking the big and small of it. It's like saying you can't hear ultrasonic sound, but it still exists anyway, and we can create it. You can't hear. Yeah, they are related. You cannot detect a gravity wave from 20 tons of concrete moving. But if you have two 20-ton balls of concrete rotating on a surface, maybe you can detect that once the detectors get better.
I don't know if they are big enough for you to actually move the frame drag. The planet Earth can do that. You know, Earth actually it's massive enough
Once,
to
once
frame
again,
drag
once
the
again, it's simply,
space-time.
once again,
But
it's
I
simply a
don't think
matter of scale.
masses on Earth can do that.
It's simply a matter of scale.
I
Remember,
know. I don't think they
remember
could.
at one time, communicate across the Atlantic Ocean required hundreds of kilowatts, and now we can do it with a few watts because detectors are better, emissions are easier, they're digital. So we just have,
And they detect ore, metal ore deposits using
yes,
gravitational anomalies.
yes. By the
And
way,
submarines and
by
submarines.
the way, Helen, how is the Chichalube meteor impact crater diameter detected?
Yeah, it was gravitational effects on Earth. When you're orbiting satellites, you can see the
Right,
difference in gravitational fields on the planet.
but that was due to the gravitational fields due to matter being denser or not as dense.
Yes.
So that same effect could be once we get gravity measurements down to a more commodity science, maybe we can measure smaller gravitational fields. And then you will find large mass items that become noise sources in gravity measurements.
Okay.
It's got to get better, obviously,
Yeah.
but I don't
Yes,
say never.
right now at this moment, what we can kind of, detect is that
Mhm.
very massive objects or very massive areas of planets are affecting space-time, and we can calculate that, we can detect that.
The other thing is it has to be at high frequency.
Yes.
It has to be energetic, and it has to produce enough frequency that we can see the ripple effect of it. Elephants can speak to each other through infrasound that we cannot detect and travels through the earth.
Yes, whales too.
Yes. So does the moon orbiting the earth produce a low frequency gravity wave?
Might.
Uh-huh.
That's interesting.
But we just don't have a detector capable of detecting it.
Yeah. I think those animals can hear like the ocean masses moving.
Yes. Well,
That's an interesting way to see.
yes.
That will be cool.
Another news item that I didn't bring up, but is kind of in the same realm of until you figure out the underlying mechanisms, you can't consider it as something regularly detectable in science. We've known for some time that birds can navigate using the electromagnetic fields of the earth. Well,
I read that one.
how do they do that? They're not seeing it visually, are they? And what they found,
don't really know, because that is a protein in the retina
I was just going
that
to say,
might be
yeah,
seen. So might be that they're not sure yet, but it might be that the birds can actually see the magnetic field lines. That
yes.
is like, what?
I was just going to mention that, yes, they've discovered that there is a protein in the retina of birds' eyes that apparently has a quantum level effect at producing photons, which means that as birds fly around, they may have the ability to see magnetic field lines and can follow them.
That's amazing. Yeah.
It's
I read that one and was like baffled by it.
Oh, I think
amazing.
it's amazing because, you never know how much you don't know until you know what you don't know.
Well, they can see it, but we don't know why they fly south in the winter,
Oh, we know.
We know because the weather. They
It
do.
gets warmer. It's
like,
easier to potty when it's warmer.
I mean, why do you think they call them snowbirds? We can't see magnetic fields, but we know what part of the year it's going to be colder up north than to come south to Florida. And we also know that, the state of Florida has this taxation.
Or some people from the south comes to north when it gets cold.
Yeah.
Except when it's a pandemic.
But they also know in Florida that you have to have 6 months residency in order to get your real estate tax deduction. So even if the weather isn't cooperating, they still have to come down here when it's warm to get their 6 months residency to collect their real estate tax.
I did not know that.
I love the thunderstorms, yeah.
Yeah.
So you guys have any more things?
I think it's been a fun session. We've dug into a lot of deep things that
Yeah.
nobody's brain has cracked open and spewed stuff. So lots of fun.
Yes. So
Anything?
anybody have more ideas?
Okay, then I'm going to stop recording.
All right.